Hi students. I'm going to attempt to be a little more focused with what we need to learn before the AP test. So this is kind of a separation from our textbook. This is going to be 10.5 on AP Classroom, and it is covered in 9.5 of your book, but in a little different way. So this is about harmonic and P-series. So first of all, a definition. Harmonic series are series that look like 1 plus 1/2 plus 1/3 plus 1/4, etc., all the way out to infinity. And harmonic comes from the same thing that you think of when you think of harmony or harmonic is from music. Is if you have a guitar string that is resonating and then you cut it in half. And I'm pretending right now because I know nothing about music, but this is what harmonic comes from. That name harmonic series comes from. And oh, look, some more music. I know nothing about music, but some of you might be relating to these images right now. So that's what the harmonic name comes from, but the thing that you need to know as calculus students is you need to know the name harmonic series because it comes up a lot, and also that the harmonic series diverges, that there is no sum if I add these up. If you remember the nth term test, the harmonic series, the terms are getting smaller and smaller and smaller. They're going to zero. Your terms are going to zero, but they're not going to zero fast enough, in essence, for you to add them together and get a number that's not infinite. I'm going to show you why, but the big thing you need to know is that the harmonic series diverges. The reason, if you remember last chapter when we were looking at the graph of 1 over x, we said, well, maybe we could find all the area under this graph, all the way out to infinity. And we said, maybe we could. If we could, that would be an improper integral for sure, but maybe it has an answer, or maybe it diverges. Our harmonic series is a bunch of rectangles that fit below that curve, or actually they kind of overhang that curve if we do left endpoint. They're just a little tiny bit bigger, so if I add up the area of all these rectangles, it's going to actually be a little bit bigger than the integral, because the integral would be the area actually under the curve, and the rectangles are a little bit taller than the curve, at least if I draw them this way. And I hope you agree that the area of the red rectangle is 1, because it's a 1 by 1 rectangle. The area of the orangish rectangle here would be a 1 by 2, so it would be an area of a half, and the light green rectangle would have an area of a third, etc. So all of those rectangles together would be the harmonic series. So if the area of those rectangles is finite, then the harmonic series converges, and if it's infinite, then they don't. Then it doesn't. So what we're going to do instead is we're going to take a look at the area under the curve. So we're going to look at just the integral of 1 over x. And if you remember, when we did that integral last chapter, we would do the integral and we would turn it into a limit, so it would be proper. We'd say, well, I want to do the limit as b approaches infinity of the integral from 1 to infinity of 1 over x, and that's going to give me the area under this curve, which will be a little bit smaller than the sum of the harmonic series. But if I do the antiderivative of 1 over x, I get natural log of x, and if I'm going to do the limit as b approaches infinity, well, that would be, oops, I forgot to replace this with a b, but it is a limit. So this would be natural log of b is definitely positive because it's going to infinity, minus natural log of 1. Well, natural log of 1 is 0, but the limit as b goes to infinity of natural log of b is infinity, so this integral diverges. All of our rectangles were a little bit bigger than that integral, so it makes sense that the harmonic series diverges as well. This is actually called the integral test. This is a really good test for series, but it's not on this year's AP test, so I'm not going to spend a lot of time stressing it. It's just a nice way to test whether your series converges or not. What you need to know at this point is that the harmonic series diverges, and the reason why it diverges is this integral test. You can also use the integral test to prove this theorem. This is the P-Series test, which is another thing that you're responsible for. The P-Series test it kind of looks like the harmonic series, but it's with a little tiny exponent on the denominator. And if that exponent is bigger than 1, then your series will converge. If the exponent is less than or equal to 1, then your series will diverge. And I just want to quickly remind you, if you do 1 over x to the third, that antiderivative would be negative x to the negative fourth over 4. And if you plug in infinity here, that would go to 0. So that's kind of the short proof of why the P-Series test is true. It's because of the integral test, but we are not testing you on the integral test this year. So what you need to know is the P-Series test. It's pretty limiting. It's only for series that look exactly like this, 1 over n to the p. But it is a general, it's why the harmonic series diverges, because that would be for p equal to 1. Tomorrow we're going to talk about, or Monday, we're going to talk about alternating series. Alternating series are ones where the signs go back and forth, positive to negative. The alternating harmonic series, it turns out, converges. This is a graph of the partial sums. Remember, the partial sums would be, the first partial sum would be 1. The second partial sum would be 1 minus a half, which is a half. The third partial sum would be half plus a third. And so that's what this graph is. It's a graph of those sums. And I'm not proving at this point that the alternating harmonic series converges, but maybe you can see that the terms are getting closer and closer to a value as you go. These ones are not diverging. They're not going to infinity. What's happening is you're subtracting a half, and then you're adding a third, and you're subtracting a fourth, and you're adding a smaller number. And so you're adding and subtracting bigger and smaller numbers. Smaller and smaller numbers. So you're going to converge on something. At this point, you don't need to know what the alternating harmonic series converges to. You just need to know that it converges. So here's your summary of today. You should know what the harmonic series is. You should know that it diverges. You should be comfortable with the P-series test, and for p greater than 1, a P-series converges. And then finally, and we haven't proved this yet, but we'll talk about it more next time, is that an alternating harmonic series converges. Thanks so much. Bye.